The goal of this video is to help you use the TI-83 or 84 graphing calculator to brute force certain types of chemistry kinetics problems. And as a very, very quick review, kinetics, study of two key factors, reaction rates, and reaction mechanisms. And we're going to go ahead and assume this isn't your first experience with kinetics and mechanisms. So I just want to look at a simple rate law. Rate equals K, concentration of something, to some power, concentration of something else, to some power, ... With the idea of a rate law in place, we can talk about the rate, the way things are changing in terms of reactants and products, by looking at K, the rate constant, and then the concentration of whatever species you have. And at a quick glance here, the only things that affect your K would be temperature or some catalyst, which varies the activation energy. All right? So as you're looking at changes in K, you're talking about that being changed by temperature or some catalytic change where there's an alternate pathway. What we're looking at with these types of problems, if we're going to analyze reaction rates, is how the concentration of the reactants or products affect the reaction rate. And to do so, we look at these little things here, which are called reactant orders. And it is a key feature to remember that you can only determine reactant orders experimentally, and then there's fine print, but you can only determine reactant orders experimentally, which means you're going to get sets of data like this, or maybe sets of data like this. And these are the two key kinds of kinetics problems you run into. The first of which being when you have concentrations and rates, and the other of which when you have times and concentrations. So there's a strategy we have for this, and there's a separate video we'll look at for that when you have concentrations and rates. Right now I want to focus on time and concentrations and how that affects things. I think it's not too much of a stretch to say if you see two columns of data that graphs are going to come into play somehow, and knowing a little bit about our kinetics, we can say we're going to find that reactant order by graphing, given concentration and time data. And there's three things you have to do here, which are graph it, concentration versus time, natural log concentration versus time, and 1 over concentration versus time. The reason we do that is because it corresponds to some integrated rate laws. If you have a zero-order reactant, it's going to graph concentration versus time linearly. If you have a first-order reactant, like in nuclear decay or something, it's going to graph natural log concentration versus time linearly. If you have a second-order reactant, it's going to graph 1 over concentration versus time linearly with a positive slope. So you'll notice the negative slope, positive slope, corresponding to our rate constant. And again, there's plenty of other videos to discuss those things. Our key feature here is going to be using the calculator to do this, to brute force these things. And so let's take a look at this data right here. We'll write down some steps on the side and try and make this as quick and painless as possible. I have this TI-84 Plus. This is pretty much the same for the TI-83s or any of the other 84s, but not the Inspires because they aren't as intuitive. So what do we need to do in order to utilize Graphing Calculator to do some graphing of this information and to analyze it? Well, turn it on, all right? And let me get away from there. We want to do a statistical analysis of this data, specifically in these ways. So what we're going to do is make sure we have that data entered. And what I'll do is I'll run through this once, and then we'll write the steps down and go back through either this one or another one in slow-mo, looking at the steps as we went. But it is as straightforward as utilizing your statistics function and editing your lists. And I happen to have put in L1 and L2 the time and concentration data that's listed here. All right. So this was data I pulled out of a problem from Tro's book, most recent edition. I don't know what it is, but good example problem. And we're going to graph it 3 ways. And in order to graph it 3 ways, we're going to have to know time, which I've got in L1. We're going to have to know concentration, which I've got in L2. And then we're going to turn L3 and L4 into natural log concentration and 1 over concentration. And it's pretty quick. If you're at all familiar with spreadsheets, the way these graphing calculators work is they set things up in mini spreadsheets, and then we can utilize that technology. So if you go to the top of the L3 column, if I want L3 to be my natural log of concentration, all I have to do is say that L3 is going to be the natural log of the stuff that I have there in L2. So I'm going to hit second and get that L2. And now we filled in L3. It's the natural log of all those L2 values, and we're going to use that for a separate graph. Then our L4 here is going to be our other graph. And I want 1 over the concentration. My concentrations were in L2, so I'm just going to go to the top. 1 over L2 gives us those values there. Now don't panic if this is going by super quickly, because we'll go through in slow-mo with some instructions written down, but I want to give you an idea of what it takes for right now. And right now we have all of our data that we need in the places we need it. In fact, I want to label things real quickly for our purposes here. So for our example, we have L1 as our time, L2 is our concentration, L3 was the natural log of our concentration, and L4 is 1 over our concentration. You don't have to do those things in those places, but it is good to remember what you put where. So we have the data. It would be nice if we could graph it, because our goal is to find a straight line. So we can just hop back to our stat function. Actually, we'll go to stat plot, and we're going to graph things. And those things we're going to graph are time versus concentration, time versus natural log concentration, time versus 1 over concentration. And we'll do that again. I got there by hitting second y equals. That gives you stat plot. And I want to make sure it's on. All right. So I'm going to hit it. It is on. I'm going to go down and say I want my x's to be time, and I want my y's to be concentration this first time. I could graph L4 right away, but let's just go in order. Bang. Yeah. And you can exit out of this, or you can go straight to the graphing. I think it's worth noting that when you hit graph, you may not see what you want, but the step every single time is to hit the zoom key and then choose 9, which is stat zoom or zoom stat. Now, looking at that, not a straight line. And what does that tell us? It tells us that this reactant is not 0 order, all right? We know because that's not a straight line. And there's statistical ways to determine if this is a straight line or not, but I think it's safe to say that's not straight. So what I'm going to go do is try another graph, this time time and natural log of concentration. So I'm going to go back to my stat plot, second y equals, and I'm going to change it to L1 and L3 this time. So second 3 is our L3. And we can go right to the graph then. And you'll notice you don't see it once again, because we need to zoom 9, that stat zoom. And if you look at that, that doesn't look very straight either. And it's worth noting, the way the data works out for these natural log problems, we've got a bunch of numbers less than 1, so these natural log values for our concentrations, so our natural log values end up negative. So we end up with a graph, a negative slope on the negative side of the x-axis. All right, so that's not looking too straight. Let's give it one more try. Stat plot, we're just going to edit. And I want my 1 over concentration this time, and then we just cross our fingers to hope it works. Go over to the graph, zoom 9. That looks very straight. All right. So what have we determined here? Well, we have determined that the linear graph is 1 over concentration versus time, and that is second order with respect to that reactant.